Well, thanks so much for the very kind introduction and for the invitation to speak. It's a pleasure for both Dave and I to be here. So we'll do a dual act today, and essentially I will start with a very general introduction about diamond large source and diamond facility, because as you will see, we have also a large collection of electron microscopes, which complement what we do with X-rays. I will then focus on the capabilities and recent scientific example of research in the physical sciences. And then I will hand over to Dave, who will do the same in the life sciences. And if we have enough time, we'll go through also some of the plan for the upgrade of the facility and the Diamond 2 program and how it's supposed to play out. So I'll start by, if I can switch the slide. So general introduction about Diamond. So if you've never been to Diamond, this facility is essentially located on the Howell campus. This is about 25 kilometers south of Oxford. And this campus was initially developed, like many facilities in the world, was developed after the war as part of research on radionuclide and research on atomic energy. And at least the north part of the campus was developed in this way. And then later on, so this was typically 1945 to 46. And then in 1957, the southern part of the campus on the Rutherford Appleton lab was developed. And this was initially high energy physics, but then was transformed progressively into a collection of national facilities, as well as clusters of academic government and also private companies on the campus. So the campus is already very large. You can see here the size, about 6,000 people working on the Howell campus, about 240 organizations. And essentially, when it comes to large-scale facilities, you find the ISIS pulse, neutron and muon source, which I think has been presented as part of this seminar series or webinar series relatively recently by Sean Langridge. You have also the central laser facility, which accommodate a number of laser experiments in condensed matter physics, also in high energy physics and plasma. And they are currently developing a new facility called EPAC for extreme photonic application. This is a partnership with the Ministry of Defense. There are a number of key partners to Diamond on the site. The Rosalind Franklin Institute, which mission is to benefit from the development in technology in the physical sciences to accelerate discovery in the life science. The research complex, which is located very close to Diamond, which is acting as a research hotel to support some of the research done at the facilities. And recently, the headquarters of the Faraday Institution, which is a mission-driven investment by the government to accelerate development of batteries and commercialization of new battery technology in the UK. And all around us, there's a huge array of different companies and on satellite application, the European Space Agency. The National History Museum is going to join the club with a digitalization center very soon. So that's a quite exciting and vibrant campus. Diamond itself is one of the largest scientific facility built in the UK for the last 40 years. It was established in 2002 as a legal entity between two partners, the public sector through UKRI, UK Research and Innovation, through one of the research council called Science and Technology Facility Council. And the Wellcome Trust, the Wellcome is a caritative organization, one of the global caritative organization in the world, which invests a lot in research in health and well-being in particular. And so Diamond was set up as a private company with a share of 86% from STFC and 14% from the Wellcome. All of the beamlines that we operate are owned by Diamond, even though one of them actually a series of them were built as partnership with universities, one with Manchester, another one with Leeds, and another one with Birmingham. But they are operated and fully owned by Diamond in the operational sense of the word. We have more than 14,000 researchers that have accessed the facility to date, and so it's a quite vibrant community using synchrotron and electron microscopy. The synchrotron itself, it's a 3 GeV machine. I think you've seen this kind of things before, so I won't go into the detail, but it's a 100 MeV LINAC. The circumference is around 560, so it's a kind of mid-size synchrotron with 24 cells operating with 300 milliamp of current. When it was built, it had one of the best horizontal emittance compared to other facility because it was relatively new. Diamond was one of the latest in terms of third generation machine, but it's of course now been passed by other facilities in the world that have developed fourth generation synchrotron technology. As many of these facilities, the beam is extremely stable for a long period of time. It provides very efficiently beam to users, and the MTBF, for example, is well in excess of 100 hours. We are not too focused on timing applications, so which means that this synchrotron operates most of the time in normal mode rather than in hybrid mode. We spend typically about a week per year in hybrid mode, and some other modes, for example, alpha, low alpha mode, are even used even less than hybrid mode. So most of the time we operate in this conventional filling pattern. So in terms of beamline, Diamond was built in 3 phases. As part of the initial investment, there were 7 beamlines built in 2007. 15 beamlines were added to this in 2012. So this was a second investment in the facility. And finally, a third phase of development has been completed only recently with an extra 11 beamlines. So as it stands, the facility is at full capacity, operating 33 beamlines. And what you will see here at the bottom is that in addition to operating these beamlines, we have also a very large collection of electron microscope. I will come back to this, but it's, I think, by far the largest activity combining electron microscopy in the physical sciences as well as in the life sciences with X-ray and synchrotron X-rays. The different beamlines are kind of divided in these technical and science, technique and science groups, which are listed at the bottom, and we'll talk more about this later. So in terms of the electron microscopy itself, the opportunity was to combine, to co-locate the Electron Physical Science Imaging Center and the Bioimaging Center with one of the very long beamline, the hard X-ray nanoprobe, I-14. And so this building is currently hosting the hard X-ray nanoprobe, as well as all of the microscope, as well as also the preparation facilities to actually use the microscope and the nanoprobe. In the physical sciences, we have 2, this is essentially a joint venture with University of Oxford on one hand and Johnson Matthey on the other. And we are essentially providing a service where we can do research using atomic resolution spectroscopy. So we have 2 GeoL instruments, as well as high resolution imaging. And these are accessible exactly like beamlines are accessible. So it's if you're an academic partner and you want to access the microscope, the process is peer reviewed like for other type of proposal. EBIC, they will talk much more about this, but as you can see, a very large collection of microscopes and also focus ion beam to prepare the sample, and also a collection of lower end microscope to do some preparation. You can see here the control room and the microscopes are down there. And once again, it is accessible like any other X-ray instrument. In terms of users, as I said before, we have a community reach of 14,000 users, about 180 companies paying for access. 25% of our users declare an academic, an industrial involvement in their proposal. 33 experimental stations on the synchrotron side, 10 microscope, and all of this running concurrently. We typically operate 200 days a year. We have 2 calls for proposal in April and October. So I'm sorry, but you've just missed, if you're excited about putting a proposal, you just missed the deadline for the current round. And we operate typically in 5 modes. for user access, a standard mode where you essentially apply to for a single experiment, a block allocation group, which essentially help you coordinate access to the facility with other members of other groups or other university, coordinating access and making sure you manage within your group the access to the facility. So this kind of self-manage. A long-term proposal where you can actually have the opportunity to continue the research over a period of 2 years rather than a single proposal, which gives you some continuity in your research. Rapid access to get typically conventional measurements. Usually it's limited in the range of sample environments that you can use, but conventional measurements to your research, and of course the proprietary access to the facility, which is continuously growing. In terms of industrial access, you have a group of people led by Elizabeth Schotten. So you have a group of scientists. I think the group is currently employing about 11 different scientists in different areas, and they will help you through the entire life cycle of the experiment, so to speak, from the preparation to the access to the experiment itself and the data analysis. And initially, this group was concentrating, most of the effort was in the area of drug discovery and drug development, but progressively we've seen an increased demand for developing also activities in chemistry, in catalysis for consumer products, as well as engineering. So the offer is actually much broader than it used to be a few years ago. The facility is coming to maturity. These 3 phases of building have been quite rapid, so that you can see that the number of publications that are very reason for this research is also increasing relatively quickly. And we are now with the full capacity 33 beamlines operational. We still have 4 or 5 of them that are in optimization mode, let's say. So this will continue to grow, but at some point we'll reach not plateau, but yeah, maturity, I would say. Typically at the moment we are publishing our users, and this is just academic users, are publishing between 1,100 and 1,200 publications per year. About 35% of these publications are in journals with impact higher than 7. And it's very broad in terms of the range of science that is currently being supported, like other synchrotrons. I think this is one of the success story of synchrotron, is that it enables research in so many different fields and disciplines in the natural sciences that you can really showcase so many examples of research in chemistry, physics, biology, material science, and engineering. So that's a very, very broad offer in general. One key thing that I'm sure Dave will come back to is that the diamond has been a key player in the response to the pandemic. I think if you look worldwide on the protein data bank, to date, there's been more than 1,600 structures related to SARS-CoV-2 that have been deposited under PDB, and about a quarter of them have been done at diamond alone. When you consider that there are around 50 synchrotrons worldwide, this is a massive effort during this very difficult period. Of course, we are also looking at the impact of the facility and the socioeconomic impact of the facility. This is a recent study that has been published, which tried to use some of the methods actually developed as part of the OECD to try to quantify and monetize the impact of diamond in terms of socioeconomics. And this came very favorably with more than 1.8 billion of impact, which compare very well with the investment that has been put in the facility over the last 15 years since the start of operation. And it's a bit more than that when you count the creation of the facility itself. This study was done at a time where the facility was not mature yet, so this will continue to increase as the capacity of the facility will continue to grow. So I'll switch now the second part of my presentation for the moment to the physical sciences, and I won't have the opportunity to demonstrate all of the capabilities, but hopefully will give you a sense of some of the areas that we are pushing scientifically, but also on the technology front, and how they can be developed further in the future. So the physical science group, physical science division at Diamond is actually split into 5 groups. Paul Quinn is responsible for imaging and microscopy. Sanjit Desi is responsible for the beamline, mostly in the soft X-ray regime, but also with one beamline in the hard X-ray, looking at mostly magnetic materials and quantum matter. Joe Hiljak is responsible for the group on chemical crystallography. Sofia Diaz-Moreno is looking at core level spectroscopy, emission, and non-resonance scattering. And Chris Nickling is responsible for structure and surfaces. So I will only briefly highlight some of the science that has been done recently, as well as some of the technologies. But I would encourage you, if you have any question or if you want to know more details about the science being done in this group, to contact directly the team. I think they will be very pleased to answer any question and help you if you want to, for the first time, for example, access Diamond and create some new partnerships with some of the scientists working at the facility. So I'll start with the imaging group, and you know, if you think about imaging in terms of length scale from the you know, atomic level all the way to macroscopic object, you know, you really start with electron microscopy as a complementary tool to the X-rays. And so we're seeing an increased number of publication and research being done where the electron microscopy is actually combined with X-ray technique. So a lot of the time they are, for example, on photovoltaics research, there's a lot of correlative microscopy happening where the combination of electron microscopy to look, for example, at defects at the atomic level, hard X-ray nanoprobe, for example, to look at strain and chemical mapping at a nanoscale level, comes together to give a full picture of the science and pushing really the technology. We also push collaboration and partnership in the sense of development and technique development. And for example, tachography, which, as you know, is, has been initially thought about in the context of electron microscopy, which is now coming back with a vengeance in the X-ray world, is also something that we're developing in coordination with the electron microscopists. So one of the benefits of collocating the electron microscopy with the X-ray is the ability to have critical mass and to push some of these pipelines for data analysis, which are common between X-ray and electron microscopy. So this is an example of some of the low dose electron microscopy they do on semiconductors when they look at line defects. And actually the reconstruction that we are using to look at this particle material is exactly the same as what we developed for X-ray science. In the soft X-ray regime, recently we had for quite some time a stick-sum beam line, but recently we are also pushing a new branch line, which is dedicated to tachography. It's called J08, so it's a second branch of an existing beamline. We see some early research done by Claire Donnelly and a group looking at ferromagnetic domains into, in this case, this is a test sample with cobalt iron. So this beamline just came online very recently. And so pushing them, once again, tachography to look at higher resolution imaging of in this case magnetic domain, but also research that you can apply to virtually every field of science. In environmental science, in chemistry, you have very similar problem with very similar length scale. This is using actually the new generation of scientific CMOS camera, which are very efficient, very impressive. And we, as I said before, we are really pushing the automatic reconstruction of this kind of imaging experiment, because the user at the end of the day, what we are interested in is getting almost in a live fashion access to the data and to the not only the data but the physical space of interest, so to speak. The hard X-ray nanoprobe I-14 in this group is also a relatively new addition to the capability at Diamond. This is typically one of these very long beam lines that you find at synchrotron, because you need to demagnify the beam. And so there are many beam lines like that in the world now. I-14 is one of the newest in the club. reaching typically around 50 nanometer resolution and pushing it down to 25 to 30 nanometers when they use tachography. This is one of a recent example of research on photovoltaics. As you know, there's been quite a lot of activity in this space, where scientists in the last 10 years have very quickly developed technology to use halide perovskite to improve the efficiency of photovoltaic devices compared to silicon. You probably have heard about this tandem cell, and actually some of them are already commercialized. And this is a study where they try to correlate the defects in the concentration of bromide inside the material at a nanoscale so essentially to try to map the defects, the chemical inhomogeneities, the strain, and the composition, and map that with experiments that they do with other techniques, so photoluminescence and also electron microscopy in this case, and trying to get a full picture of why this defect essentially drastically reduced the electronic response of this material and how the electronic disorder is actually introduced in this system. So this is one of an example of where correlative microscopy is actually very, very useful. We have a beamline I13 with two branches, another very long beamlines, one dedicated to imaging with phase contrast imaging and full field microscope. We have another one with current imaging, and I won't go into the detail of the research, but some studies of particles that have been emitted in the Fukushima explosion, and try to understand, how uranium oxide is actually present in these microparticles. Different type of imaging modalities where scientists use ping beam and phase contrast imaging to look at strain on the nanoscale in different material, in this case bones. So this beamline is actually going to, really enhance its capabilities when we push the technology with the new synchrotron. And then if you go all the way to the kind of macro scale, this is another recent example of research which has been done on this skeleton, the Littlefoot, which is one of the oldest homoids, which was found in South Africa. This is 3 million years old, and researchers are done this high resolution tomography of this skull, and in particular the teeth and some of the blood vessel in the brain to try to understand, at which age, for example, this homoid died, what was the diet, was he affected during his lifetime, how is the structure of the brain different to what is happening in humans at the moment. So something very different to photovoltaics, but something also very interesting in the field of cultural heritage. So this is the imaging group. I'll switch now to magnetic and quantum materials group. I guess one of the new baby in the suite of instruments that we have at Diamond is this soft X-ray RIX beamline. This is a technology, as you know, that has been really pushed in the last decade, going from typically something around an electron volt energy resolution down to typically 30 milli electron volt nowadays at the copper edge, and even lower if you go to oxygen edge, for example, you can reach 15 MeV. And this beamline is very impressive in terms of count rate. Of course, you can look at all sorts of local and collective excitations in solids. In this case, this is a recent study in Science that has been published earlier in July, looking at collective excitation in a superconductor, which is a neodymium nickelate, which is, as you probably know, very difficult to, this is new superconductor, which was very difficult to synthesize. I think people have spent more than 20 years trying to do that, and trying to look at similarities between the excitation in this system with respect to other superconductors, for example, cuprates. This beamline is not only useful in terms of quantum materials and looking at collective excitations in solid or in condensed matter physics, but also very interesting when it comes to understanding some of the properties of, for example, battery materials. So these are alkali-rich materials for battery research. And in this particular case, there is a very famous problem known in this family of compound where there is a fading during the first cycle of voltage hysteresis in the system, with probably the creation of defects. But these beamlines essentially gave access. So with using RIX, you can actually use RIGS to probe the material doing some sort of vibrational spectroscopy to look at the formation, in this case, of molecular oxygen or something very similar to molecular oxygen, extremely weakly binded to defects that are created in the solid during the first hysteresis cycle. And you can use RIGS actually to quantify the vibrational modes that you have in this weakly bounded oxygen. So this is something which is also quite interesting, and a new application of RIGS, which has been also done by other groups and other synchrotrons. In quantum materials, there's a lot of activity trying to understand topology in real space. And in particular in antiferromagnets, trying to understand defects and how topological defects can be created and annihilate when you either apply a magnetic field or you do a ramp up in temperature. This is a recent example of a very beautiful structure that you can stabilize in iron oxide, a very simple oxide, iron 203, stabilizing this kind of meron. So this is essentially half a skyrmion. That's the best way to describe it, where you have, which have a topologically non-trivial structure and they appear in pairs in the system, and they can be easily annihilated by a magnetic field or an hysteresis in temperature. And this can store actually potentially information at a very small scale. And it's a very interesting system because iron 203 is relatively simple to make. So this is topology in real space, and something that we see a lot of example of. This is done using photoemission electron microscopy, X-ray beam, but also you can start to look at this thing using current X-ray imaging, which is the next step, I think, in the journey in this material. And so this capability will be extended even further, because now we've just received and installed an aberration corrected beam. This is Francesco on the beam line. Maccherozzi on the beamline, being very happy with his new instrument, and this will push the resolution even further to typically, we hope, below 20 nanometers. In structure and surfaces, we're continuing this journey on topological system. There is also a lot of research being done on topology, not this time in real space, but in momentum space, where you have featuring the dispersion of band in solid, which makes non-trivial topology, in this case, veils. You can see these crossing points here, these veil points, which are essentially low energy excitation, which are the non-topological signature. And these are systems that have very high mobilities and which can really transform the way we use electronics in the future. So this system, this was done using ARPES. This is in a structure and surfaces group. And in this particular study, you can see in principle, with no chemical doping, this veil point is not observable. It's well above the Fermi level. But by doping the system, you can actually push down this veil point, this crossing point below the Fermi level. And so there's a lot of activity, not only studying this material, but trying to dope them in situ without leaving the beamline, and then recollecting data to see how the effect of such doping or chemical modification can affect the properties of the system. We're seeing a lot of research in this area, and even more so because of the advent of two-dimensional research on two-dimensional materials. So one thing I would like to flag in this space is the recent installation on the nano-ARPES branch, which is one of the capabilities we have at Diamond, for a new generation of optics capillary mirrors, which enable to really focus the beam at the moment down to 5 micron. And we hope in the next few months we'll be pushing this down to 2 micron, where you have fluxes which are in very large excess to what you can do with zone plate. So factor 30 more than zone plate. We're seeing a huge demand for this kind of research on two-dimensional materials. There's also a lot of research where people want to gate the system, or they want to apply strain, they want to look at nanotexture, and of course, really study all the materials that are not necessarily easy to look at with ARPES, because their surface state is not easily prepared. Continuing with ARPES in the surface group, we've also recently added the capability to do higher energy, so AXPES and also soft X-ray ARPES. And this is a very nice capability in the sense that you can really probe this 4-dimensional momentum energy space without having necessarily access just to the surface, but probing matter which is deeper than what you can do with UV ARPES. You're not so sensitive to the defects of the surface, which open up opportunity for many different applications. And another beamline which has been in this group, in the surface group, just recently installed, it's BO7. So this is a bending magnet beamline. This is another beamline that will benefit a lot from the installation of Diamond 2, because they will be able to switch at least one of their two branches to an insertion device. It's a beamline where you can do a near ambient pressure XPS, but also recently a NEXAF and high throughput XPS, which have been just commissioned and are currently being open for experiment. This is the new beamlines with high throughput XPS with a very highly automated in vacuum sampling handling system. And this is the NEXAF end station that are going to be soon commissioned and open in the scientific program. In spectroscopy, I would say a lot of the work that we do is dedicated to kind of core level spectroscopy. There's a lot of application in chemistry, in physics, in material science. A lot of very nice example of research in this space. This is an example on the B18 beamline, where they looked at jarosite, which is a mineral which is present on the surface of Mars, and trying to understand the formation of jarosite in very deep ice sediment, more than a kilometer down in the Antarctic, where we don't quite understand how jarosite is actually formed. And what you can learn from what's happening on Earth is essentially important to try to explain what's happening on Mars, and in particular the weathering effect that you see with these kind of minerals. So we see a lot of studies in this space, in mineralogy, in chemistry, and in physics. In chemistry, there's a lot of work actually being done at the moment to try to understand how to improve catalyst. I don't think it's unique to diamond. This is an activity, of course, which is pushed all over the world. This is a recent example of using commercial zeolite and trying to enhance this functionality by adding tantalum and aluminum to this host structure. And the reason I'm flagging this particular study is that what we're seeing more and more, and I think it's once again not common to diamond, but you can see that across the board, is the combination of different modalities when you do research like that, where scientists want to combine ZAS, XRD, in this case, inelastic neutron scattering and DFT calculation, to actually understand how these materials and these catalysts in this case are improved when you modify it chemically or by other means their properties. And finally, in spectroscopy, the one modality that we have more and more demand for is the utilization of emission spectroscopy. And with this is a recent example looking at oxygen deficient perovskite and trying to understand using emission spectroscopy the difference valence state, where you have access essentially with this K beta line to the spin state, and trying to understand how these different materials are actually working when it comes to oxygen reduction capacity. And so this is all studies that are done in situ. And as I said, doing EXAFs and XANES and emission at the same time, but really more and more demand for this kind of emission spectroscopy. And so to this point, one of the area where we are investing relatively large sums of money at the moment in the spectroscopy group is to open up fast emission capability in a very large energy range. This is using two spectrometers that we are currently developing for I-20 and I-18, which will really push emission spectroscopy capability, especially for radioactive materials. So images, for example, of uranium and so on, chemistry at the sulfur edge, and environmental science at the phosphorus edge. And this particular spectrometer will be also able to do two emission lines at a time. You can see there's two focus points, probably not obvious from here, but there are two detectors with two focus points where you can actually use this new capability. In terms of radioactive material, and that might be of interest for you if you're looking at waste or waste disposal, on research on actinide or lanthanide, We have now a new building that has just is finished, a new materials building, which has been actually a grant investment for the from the National Nuclear User Facility, which is a government initiative in the UK to speed up research in nuclear research. And this is a new capabilities. We have a Diamond 2 with storage room, counting room, wet lab, dry lab to actually handle, prepare, store safely, and prepare for all of the experiments that have to do with radioactive material. And this is just next to the spectroscopy beamline, but also not uniquely used by spectroscopy beamline, but also for example, bounded diffraction and single crystal diffraction. And finally, I'll say a few words about crystallography. There's quite a lot of push, of course, for operando and in situ science when it comes to crystallography. A lot of research on battery materials, a lot of research on MOF. That's been the case for a long time. Maybe something that is unique to Diamond that I would like to flag is the existence of this long duration experiment facility on the I-11 beamline, where essentially you have a rack of samples of different reactors, so to speak, that are where reaction are taking place. It can be a battery cycling, it can be some cement drying, it can be some humidity chamber, and you can store different sample in these containers and cycle them or change the condition or the operating condition of this equipment. And maybe once in a week or twice every week, you will collect some diffraction pattern and look at the long-term evolution of this material under these conditions. So this is in addition to the much higher throughput and more conventional bounded diffraction capabilities, but this gives rise to very interesting research. For example, research on battery. I don't have to go go through that today, but looking at the increased damage in some of the NMC materials for batteries that are happening after a long period of cycling, so a large number of battery cycles. We have also developed a very high throughput XPDF. This is the instrument that Phil Chater is responsible for. There's a robot that can handle sample. We can do operation at room temperature, but also at high temperature. And there's more and more demand for this kind of looking at disordered material with the PDF technique and combining that with spectroscopy, with also other form of diffraction to look at long range order. And a lot of demand also for experiment on MOFs, but also battery research. This is another example looking at partially disordered clef rates and how the lithiation pathways are actually happening in these type of materials. In single crystal, small molecule crystallography, there's also a lot of demand for high throughput measurements. This was one of the first structure which was actually collected after we installed the robot, which is essentially pretty much a copy and a translation from what has happened in the field of macromolecular crystallography to actually chemical crystallography, where we have higher and higher throughput. And this first structure was very interesting. It's an anti-aromatic wall nanospace. These are usually structures that are very, very reactive and very unstable, but they were able to actually stabilize this structure and actually collect the data on I-19. We are pushing really the technology. We are pushing the technique in order to be able to do faster and faster measurements, in particular with implementing new detectors, for example, cadmium telluride detectors, on these beamlines, and we've recently achieved typically data collection time that are below 30 seconds for a full single crystal diffraction, and that enables now to look at really system extremely fast in, for example, a gas environment or non-ambient condition. And I think I'll stop here. I've used already quite a lot of the time. I'll hand over to Dave, who is going to showcase some of the capabilities in life science. And if we still have some time, I'll talk about Diamond 2 later on.
Thank you very much, Laurent. It was a nice talk. And we wait for David to share his screen.
Okay.
And then we'll take the questions.
Should I just get going?
Yes.
Okay, can you see my screen?
Yes.
Great. Okay, well thanks, Laurent, and I'll try not to repeat too many of the things you said. A lot of what you said applies equally to life science. If people want to pursue possible collaborations and discuss things, please get directly in touch with the people involved. Thanks. I'll just say a couple of minutes, give a couple of minutes at the beginning of discussing the impact of the pandemic on Diamond. And there was already, before the pandemic, there was a significant remote use of a number of the beamlines at Diamond. And that really helped us to carry on with operations on a number of the beamlines through the whole thing. And we accelerated the rollout of automation and mail-in access to a number of beamlines during the pandemic. That also meant that we were in a good position to collaborate and do work on structures of the SARS-CoV-2 proteins, as Laurent has alluded to. I think if you just look at the crystallographic structures, probably about a third of them have come from Diamond. It's interesting, a significant amount of the structural work on SARS-CoV-2 has been by electron microscopy. And of course, the majority of that comes from distributed labs around the world. But again, a fraction of that comes from the EBIC Center at Diamond. And it was because of good international links, especially with China, that we were able to kickstart the work in Diamond and with external collaborators on the SARS-CoV-2 structures. So here you can just see the impact of the pandemic in terms of knocking down the number of visits to Diamond, but also at the same time zooming up the percentage of remote access. The picture on the right just sort of makes the point that in terms of the number of structures for proteins deposited in the protein data bank, Diamond is a pretty successful player and deposits, is responsible for a lot of the structures deposited in the PDB. In terms of the effect on the type of experiments, what I've talked about in terms of automation applies much more easily to relatively straightforward and standard experiments. And if you look at the impact on physical science experiments, particularly those that are more complex, it's been really more challenging to build those back up again. Industry activity, again, a lot of that is pretty routine, and industry, they were very keen to get back engaged. The industry activity built up rapidly, and actually last year was one of the best years for the industry use of Diamond. And there was clearly a lockdown when there were no staff on site, where things really slowed down. But essentially, there's been throughout 2021, there's been a continual ramp up in activity on site at Diamond, and we've worked hard to try and facilitate that. There's been a lot of challenges around it, but that we've redesigned the office layouts and worked very hard to make the working environment as safe as possible. But as I say, there are a number of challenges which I won't go into. All facilities have faced similar problems. Perhaps one of the things that Diamond did in a very concerted way that not every facility did, we set up in the early days, aided by discussions with people in the Department of Medicine in Oxford, we set up two sorts of testing: lateral flow testing, which is set up in the atrium of Diamond House, and that's targeting users, contractors, and visitors. It's very quick. People come in, they get the result within 30 minutes, and that's a very good way of picking up people that are highly infectious. But for users that are, for staff that are routinely coming on site, we have a PCR testing where people pick up the testing kit on the way out. In the morning, they pop the vial in the box. The test gets run during the day, and by about lunchtime, the results are out. And now there's approaching 10,000 PCR tests being run. Interestingly, we've had 8 positive tests so far. And despite that, we've seen no cases of on-site transmission within Diamond. These positive cases that we picked up were early, they were pre-symptomatic. The people later went on to develop symptoms. So we think this has actually been effective. And we're seeing a gradual increase at the moment in the number of tests that are being done. And this is in the context at the moment of very high levels of transmission in the UK, and especially at it seems, driven by children, and it is very noticeable in the Diamond area at the moment. So that's the COVID issue, and I'll come back and mention a couple of bits of COVID research. But just to sort of step back and look at the history of things. If we go right back to the first application of synchrotron radiation to biology, that was in 1971 in a bunker at Daisy. Ken Holmes was one of the leaders of that, and actually at that point, Gert Matelik was sort of involved in encouraging this work. And it's Gert that then went on to lead the construction and delivery of Diamond. The buildup of life science at Diamond has really been helped by the support from Wellcome, and Laurent mentioned that they're our minority shareholder, but they've had a big impact in supporting and really helping the development of life science. And the build-up in Diamond in life science was led by the first life science director, Louise Johnson, and Gert Matelik was a fantastic supporter from the beginning. Now we've got 12 beamlines in the life science portfolio, and also as again, as you've heard already, one of the strongest cryo-EM centers in the world. And I should say that, you know, the physical science beamlines do a lot of life science experiments. The life science beamlines also do experiments. The infrared and ultraviolet beamlines probably do 50-50 life and physical science. So it's a bit of an arbitrary distinction between these two, but we try and sort of think of the major drivers for the beamlines are delivered for biology for the life science, so-called life science beamlines. And the biology is pretty broad, and obviously I haven't got time to go into the breadth of it, but there's biomedical science is probably the biggest single driver, but also biotechnology, food security, the green agenda, etc., are all sort of important drivers for what we do. And you know, if you tot up the beamlines and the large number of cryo-EM machines, as you'd expect, a lot of the papers coming out from Diamond are in life science, nearly half of them. I just want to make the point that synchrotrons have really helped change the life science landscape, I think. And similarly, the life science activity at synchrotrons has helped change some of the synchrotron activity, I think. So the bag application system, which was pioneered at the ESRF, is widely used across life sciences and also in physical sciences now, to allow predictable access to groups of users to really help them accelerate their science. and it's been supplemented by complete automation, especially in macromolecular crystallography. So the automation has been led largely by MX, and it's reached the level now where users enter the sample information on the Diamond web server, they print out a label which they attach to their dewar, and Diamond arranges for the dewar to be picked up, shipped, and the results can appear back in the web server for the user within a few days. And remote access and sample mailing are operating across all three of the life science groups within Diamond now. And this sort of drive for efficiency and automation does make a real step change in delivery. So in MX, on one of our beamlines, well, several of our beamlines now, you can collect up to about 700 data sets automatically in a single day. And that then alters the approach to basic science. So the academic users can tackle more difficult problems that otherwise they would just sort of have to give up because the chance of success was so low. So it opens up really challenging problems. And for industry, it means that the rate of production of results means that methods like compound screening for drug discovery can be really built in as core to the one of the core drivers of drug discovery in the pharmaceutical industry, and all of the major pharma companies now do this. So the change in the life science landscape, the message here is that technical innovation has been driving science, and that's widely recognized, and that recognition has led to setting up firstly a research complex next to Diamond to bring scientists to the campus, and also very recently, as Laurent has mentioned, the Rosalind Franklin Institute, which is led by Jim Naismith, aims to drive the translation of physical science methods into life science. And I should say Diamond is a founding partner in the Franklin, along with 10 universities. And we're very closely working with the Rosalind Franklin Institute, and Gwyndaf Evans in life sciences is leading that coordination. There's particular areas of development across the piece, really, from large volume electron imaging through mass spectrometry, chemistry, and artificial intelligence. So this raises the question that what will this do? We expect the revolutionary changes to continue, and I think we all agree that machine learning, artificial intelligence will be increasingly center stage in the developments over the next years. And our aim is to keep Diamond on that stage. What the impact on biology will be, it's hard to predict, but I think from my point of view, I look forward to a revolution which will link cell and molecular biology together in a seamless way. And I think that linking of molecular level through to the cellular context and the tissue context will bring potentially massive knock-on changes for biology and for medicine. And I think we're really looking to have a reinvention of pathology at the molecular level, which will alter the way medicine is done. So quickly to go through the science groups in life science. So micromolecular crystallography is led by Dave Hall, soft condensed matter by Rob Rambo, and biological cryoimaging by Martin Walsh. And I've got two deputies because I'm only part-time in Diamond, Martin and Gwyndaf Evans, who I've mentioned already. Go through the activity in macromolecular crystallography. There's 7 beam lines plus some other activity, and I'll just mention that there is, in addition to the beam lines, there is an XFEL hub which is led by Alan Orville, which really aims to help the UK community, because we don't have an XFEL yet in the UK, helps the UK community prepare and engage in XFEL science. And this is really very effective. It also has the advantage that the sample preparation methods for XFEL work in life science are also very relevant to serial crystallography methods at the synchrotron. So there's a natural synergy here between Alan's group and the groups on other beamlines, particularly Robin on I-24 and Mike Huff on VMXI. So I won't go through the details of the groups. I'll just pick out a couple of highlights. This is just to say that now past 10,000 PDB depositions from Diamond. The reach of MX is quite broad. This ability to just ship in dewars means that it's really accessible to people outside of the UK. Having said that, with the present sort of problems in supply chains and shipping and Brexit, we have had issues with dewars being delayed or going astray, but we're working very hard to prevent that sort of impacting on people who want to send in samples. So there's a significant use from groups around the world. And as I said, what we can offer people is unattended data collection, but also people can do the experiments remotely. And there are specialist beamlines, which I'll say a little bit about in a minute, where it's really worth discussing with the individual principal beamline scientists if you want to use them. That includes the XChem's fragment screening, serial crystallography, and some of the long wavelength work. So just to sort of give an idea of the impact of the unattended data collection, this is a case study. Dave Hall made this slide, and this just shows how by being able to rapidly stream these things through, it was possible for the users to map the interactions of antibodies with not only the original early pandemic strain of the virus, but alpha variant, beta variant, gamma variant, and delta variant, to really get a fantastically detailed understanding of the mechanisms of neutralization and the mechanisms of sort of immune escape that occur here, and essentially produce a map of antigenic distance for the different strains of the virus. And all of this was done without users being on site. It was a very close collaboration between Diamond and the groups in Oxford. And that's so far resulted in a series of 5 papers in Cell in 2021. The XChem facility I've mentioned, which is where up to about 700 data sets can be collected routinely in a day. But it's much more than just automated data collection on the beamline. It involves a lab where many hundreds of crystals are soaked in fragment libraries. So there's automated ways of projecting the individual compounds from the libraries into the drop to soak in the crystals, semi-automated ways of mounting the crystals, and that's then linked up with the automated data collection. And this is something that is in great demand from academic but also industrial users. And so far there's been over 16,000 crystals screened via this method for the SARS-CoV-2 projects. And I'll just say a little bit about the SARS-CoV-2 work with XChem. There's been a variety of different campaigns done targeting a wide number of different potential targets in the virus. It's just really astonishing the level of coverage that's been achieved. You can see the different targets here in the table. The type of work that's gone on is varied. There's a significant activity gone on where existing drugs were investigated to see if they could be repurposed to be effective against SARS-CoV-2. The result of this was somewhat disappointing. None of them were extremely potent. However, in particular, the collaboration with Exscientia has progressed, so they have used their AI-driven drug discovery platform to take that initial information and drive it through to much more potent inhibitors. And they've just attracted a total of about $70 million from Gates with equity investment to take that forward. And that's just one example out of a number of threads of activity going on. But also the fact that results came out very early on in the process and were released on the web immediately led to a whole sort of moonshot project, as it was called, which was global in its reach and involved medicinal chemists, companies that make compounds, giving giving time and money to the project to keep it going, which started from scratch, started from no knowledge, built up from fragments to leads, and is now just entering the stage of preclinical development with significant funding from Wellcome to a variety of groups around the world to take it forward. If this carries on, the expectation will be to go into clinical trials some point, perhaps the middle of next year. So that's just a flavor of the activity. What I've talked about are really sort of standard beamlines in MX, but we've pushed the envelope a little bit. One of the beamlines that we've had for a while is using an in-vacuum sample environment to enable the use of longer wavelength X-rays to probe, to help phase proteins. That may be less essential now in the alpha fold era, but what it can do is to really light up lighter elements and solve some interesting biological puzzles. Some beautiful work on the ribosome was published a couple of years ago, but there's a continual stream of cases where people are getting deep down to understand the biology by being able to light up elements. So on the right is an example from LMB Cambridge, where the role of phosphorylation and the exact phosphorylation that controls the biology of this protein was unraveled by David Barford's group. Then the final thing is something that's just coming online, and this is a really challenging beamline led by Gwyndaf Evans, where he's trying to work with a micron-sized crystals, micron-sized beams in vacuum with high energy X-rays to really revolutionize what you can do with microcrystals. And we thought that there was at least an order of magnitude improvement to be gained if one did this. And just now this is being demonstrated. On the left, what looks like a blank picture with a few bits of specks on it is the diffraction pattern from a 3 or 4 micron crystal. And on the right, you can see the zoom up of that red dot. You can see the background is essentially 0. You can see what would normally be a diffraction spot lost in the noise now stands out very clearly. And if we look at the data that you can get from this beamline, this is comparing it with the previous generation of microfocus beamline, which was called I-24. The published analysis of this structure required 20 crystals and achieved a resolution of 1.9 angstroms. Now, using cadmium telluride detector, high energy, a single crystal can give 1.3 angstrom resolution structure, orders of magnitude better. and the quality of the map is astonishing. You can see, start to see hydrogens now in the structure for this minutely small crystal. So this is a real demonstration that there are still improvements to be made. I'll finish MX just by pointing up that we're really looking forward to a collaboration between Diamond and Max4 to build a beamline, and you can see the space there called MX Bridge. And the aim of this is to have an ultra high throughput beamline to mitigate the loss of MX to the UK community during the dark period. The use is so intense; it'll be hard to keep their activity going. Otherwise, it's aimed at both academic and industrial users. And this will have benefits, certainly benefits to Diamond, and I hope it will have benefits to Max4 as well. The soft condensed matter group is Rob Rambo, is a really diverse set of beamlines going from infrared, ultraviolet, through to small angle scattering, wide angle scattering. And we try and develop some unique capabilities. The circular dichroism beamline started off as a fairly routine activity, but has really developed the specificity of high resolution mapping, imaging of the circular dichroism effects, which has turned out to be really important for chiral structures. So there's now a lot of demand from physical sciences for this beamline. Similarly, the infrared activity is focusing on the use of advanced optics for full field imaging, but also near field imaging using an atomic force microscope to really achieve super resolution infrared microspectroscopy. And the small angle scattering is one of the beamlines, is very diverse, 50% of the activity, physical science. The other is more high throughput small angle scattering, where most of what it does is biological SACs. Rob Rambo's idea for this in the transition to Diamond 2 is to really introduce firstly some new modalities, which is X-ray footprinting mass spectroscopy, where it's possible to map protein-protein interactions and protein-RNA interactions in a very rapid way at the synchrotron, and get where you're looking at the abrogation of reactivity with water by the protein-protein contacts. This is something that's not available in Europe at the moment, and Rob is looking to bring that online, and also is looking to attach little gold nanocrystals to proteins, and thereby directly read out with a very wide energy range beam. You can read out, as you can see here, the diffraction spots are just darting around on the detector and giving a direct readout of the movement of the dynamics of an individual protein molecule. So there's some very exciting possibilities for the future. But the real drive with Diamond 2 is to drive the cost of experiments down, to reduce the risk and enable a much greater uptake of these methods. To finish with the bioimaging group, this is Martin's Walsh's group. Laurent's mentioned the EBEC activity. We also have a soft X-ray microscope operating cryo imaging modality, which is linked with a cryo structured illumination super resolution light microscope to give correlative imaging of fluorescent probes in the context of the morphology revealed by the X-ray tomography. This is now really giving some rather beautiful results, particularly for things like what happens when cells are invaded by pathogens. And of course, this linking of imaging modalities applies also to the electron microscopy. The idea is to here extend beyond the standard use cases of single particle work to do tomography and correlative imaging. I should say that there's a lot of industrial interest in cryo-electron microscopy, and we've got a very, very powerful partnership with Thermo Fisher Scientific, who have provided the instruments, dedicated instruments for industrial use in diamond. Laurent's also mentioned the ability to do FID milling. So what this means is that we can machine down cells, living cells. And this means that for the future, the revolution that occurred over the last 7 years or so in so-called single particle analysis will carry on and is part of the landscape now, well established. But going forward, we think there's opportunities for extending the power of tomography, particularly by integrating it with this correlative approach and being able to image structures in the cell. And I'll just give one example of that from work, a collaboration between Sarah Gilbert and Peijun Zhang in diamond. And this shows a cell that's been infected with the Chadox vector and has started to produce the SARS-CoV-2 spike on the surface. So this is really important to be able to see what happens in cells, make sure that the vaccine candidates are properly presented on the cellular surface. And by averaging these spikes, it's possible to get now approach atomic resolution. You can't quite get there yet, but you can see the molecular details of the spike of the vaccine candidate presented in the infected cell. And I'll just finish by saying what we haven't discussed is the data side of things. This is something that we should be thinking across all of the facilities, I think. Just EBIC that I was just talking about is already producing several petabytes of data per year. We're going to have to really think how we optimize the data that we collect, how we optimize the storage of that data, and how we make the most of the whole process by embedding AI and machine learning throughout the sort of our activities in these large-scale facilities. And I think that challenge is something to tackle at an international scale. I will stop sharing and hand back to Laurent.
Thank you, David. That was very informative talk. And thank you, Laurent, also for the talk. And I request all the audiences to thank once again our speakers. And if anyone have any questions, because I have a couple of questions in the chat panel, but if someone has questions, they can just.
It's a case if there's any value in Laurent saying something for a couple of minutes about Diamond 2, I think.
Yeah, I think that'd be really interesting. I'd like to hear about Diamond 2. Yeah, that's exciting next step. And you mentioned also MX Bridge, where Max 4 will help out in the dark period. So it'd be really cool to find out how this comes.
Stephen, do you want us to do that? We realize we are a bit late. That's the danger of asking, 2 science directed to do
exactly.
5 minutes each.
I mean, if you could say something quickly in a few minutes, that'd be really good to hear about what you plan.
I can certainly say something, and then I'll try to be brief. So let me share once again. Please tell me if it's coming up.
Yes.
Is that okay?
Yes.
Yeah. So something very, very quick, and maybe it's something we can discuss later on. So before we start to discuss Diamond 2, The next phase of Diamond is actually has to do with actually some of the remedial work that we have to do on the roof, which is actually kind of damage. It has to be replaced. The activity will start very soon. And we're taking this opportunity to put 1 megawatt of solar panel. We tried to get some of this tandem cell, but we couldn't get them in time for this upgrade. So the idea is to generate about 1 megawatt of electricity savings from this array of photovoltaics. And we are thinking about a second phase, which is not funded yet, to actually cover the entire roof with PVs, which will actually generate about 10% of the electricity usage of the facility. So Diamond 2, I think there's no big surprise in the sense that every facility in the world is trying to push to fourth generation synchrotron, squeeze even more the electrons in transverse phase space with an offer which will increase the brightness by 2 orders of magnitude, in some cases even 3 orders of magnitude. We know the current success and the recent success of the SRF in the upgrade. Of course, Max 4 was the first one, 2016, and also some greenfield projects such as Sirius. So essentially, in a nutshell, if you want to remain, I think, a science superpower in synchrotron-enabled research, you will have to do something about it. As I said in the introduction, there's around 50 synchrotrons worldwide, and 22 of them, including all of the major ones, are actually planning a 4th generation upgrade. So the race is on, so to speak, to maintain leadership. For us, this journey started really in 2018, a lot of consultation with the communities. We then developed the science case, which is published on the website. You can find it at this address. We then developed the CDR previously last year, and then we went through a number of gateway reviews. So I guess what is different from maybe other facilities is that what came out of this consultation with our community is 3 things. Number one, the community was very excited about some of the new capabilities offered by low emittance lattices. So increasing brightness and coherence for imaging application, for nano-focusing of the beam, etc., etc. So, of course, a large part of the community was excited by that. But not only, clearly in the UK is a very active community when it comes to synchrotron research, and we wanted to increase also the capacity, if possible, of the facility. And also, there's a big drive, as we've seen all across, for higher energy experiment, as well as operando and in situ science. So the third point was really to maximize the flux, the photon flux of higher energy. So the upgrade is different to the other upgrades in the sense that this is the current cell. This is a double band achromat. The new cell is a copy pretty much of the ESRF design. So this is based on the 7-band achromat of the ESRF, but you remove the middle dipole. So it's called a double triple band achromat. So you have 3 dipole on each side, and the central part is actually missing. And what it means is that you can actually put another insertion device in this mid-straight point and increase the capacity of your synchrotron and offer more beamlines in the future for Diamond 2. At the same time that we're doing that, it appears a little bit counterintuitive, but the emittance goes as quadratically with the energy of the ring. So in principle, the last thing you want to do is to increase the energy of the electron in the storage ring. But actually, if you do that, so instead of pushing really the emittance down to 120 picometers, what could be possible if you were keeping the current synchrotron at 3 GeV, if you increase the energy to 3.5 GeV, you lower the emittance. So the emittance increase, so it's not as good, but you also increase the flux at the same time. And if you look, so this plot is very kind of busy, but this is the energy, the photon energy. Each bar represents the energy range in which the different beamlines operate. And the green and red curves shows the gain factor in brightness that you can get with the first upgrade, which is keeping the energy at 3 GeV with a more aggressive emittance, and one where you relax the emittance but increase the energy. And it's pretty clear when you go in this regime there's another factor 10 to be gained by actually doing the upgrade in this energy. So that we propose, that's why we propose this upgrade to be slightly different to what the other facilities are doing. And I think this design has also been done now at SLS, for example, which is also increasing the energy from 2.4 to 2.7. So it means that essentially we can also exploit, in terms of capacity, we can also exploit 8 new straight sections that are not currently accessible, which means essentially increasing the number of beamline by this amount in the future. In terms of the upgrade itself, we are refurbishing the machine, building, replacing all of the key components that, and to ensure that the current beamlines will be continue to operate. But we're also rebuilding 5 new beamlines as part of the project. And we have also a very large package on software and computing, including improvement in, development of a new data center, a package dedicated to improving data analysis of a high data rate application, and also transforming some of the kind of instrumentation control and acquisition that we currently have. We also take this opportunity to construct a new building, which will be used for the assembly of the girders, assembly of the magnets for the storage ring, and also the booster, which also has to be replaced. But we will be using this space after the end of the upgrade to actually free up some space in the synchrotron ring so that we can actually accommodate more lab space for users and for experimentalists coming to the facility. So the timeline is we have already received independent support from the Wellcome Trust, which is of course conditional to the public investment being secure. We are currently going through the formal submission of the outline business case. Actually, it's with the government in the UK. The submission is tomorrow with a review at the end of the month. We have received preliminary funding from STFC and UKRI in June 2021 to carry out all of the enabling activities. The program is due to start in November 22 and last until the end of 2030. And the current plans, as it stands, will be to have a shutdown starting in September 2026 for 18 months. And I will encourage you, if you want to know more details, to log on to this webpage, which explains in more details the upgrade program, and also list all of the beamline proposals that have been submitted and reviewed by our scientific advisory committee and industrial committee. And you have the science case in full, as well as the TDR, as the conceptual design review for the machine. And I'll stop here.